An observatory still under construction at the bottom of the ocean may have just seen the highest energy neutrino ever detected. Today we will come to understand how such detections could show us the origins of the highest energy particles traversing our universe. In the dark abyss of the Mediterranean Sea, an array of what promises to be the world's largest neutrino telescope, KM3-NET, the cubic kilometre neutrino telescope, is rapidly taking shape. The ARCA array of KM3-NET envelops more than 1 cubic kilometre of seawater, more than 3 kilometres below the waves. In the darkness, a 3D net of photodetector modules anchored to the ocean floor captures the ghostly Cherenkov photons produced when charged particles traverse the transparent, instrumented abyss. These photons betray the fact that the highest energy neutrinos traversing our universe are constantly slamming into the Earth. At the Neutrino 2024 conference in Milan, Italy, on the 18th of June 2024, physicist Joao Coelho shook the neutrino physics community by presenting evidence that the ARCA array just detected the highest energy astrophysical neutrino ever observed. The particle was a screeching cosmological Hermes with an energy of tens of peta-electron volts, an energy thousands of times higher than the collisions at the Large Hadron Collider. Coelho offered no hints as to the direction from which the interloper came. However, such information is soon to follow and may point straight back to some of the most energetic objects in our observable universe. By illuminating the depths of the oceans, high energy particles could soon shine a light on the dark corners of our universe and pinpoint the very origins of the highest energy particles traversing it. This amazing discovery is all about some of the highest energy neutrinos traversing our universe. So what are high energy astrophysical neutrinos? High energy neutrinos are subatomic particles with energies around the peta-electron volt range, or higher, 10 to the 15 electron volts. These energies are thousands of times higher than the collisions occurring at the world's most powerful particle collider, the Large Hadron Collider. Such high energy neutrinos were predicted to exist decades ago, but were only detected in the last decade by the IceCube neutrino detector embedded in the Antarctic ice. But why are we so intrigued by these cosmic poltergeists? Well, they could help us to pin down the origins of the highest energy particles slamming into the Earth. It's a decades-old mystery where the most energetic particles hitting our atmosphere originate in the universe. Ultra-high energy cosmic rays, mostly protons and atomic nuclei, smash into our atmosphere with energies in excess of 10 to the 19 electron volts, 10 exa-electron volts. That's roughly the kinetic energy of a Djokovic tennis serve or a Ronaldo free kick, all concentrated onto something as small as an atomic nucleus. These particles have energies more than 1,000,000 times those of the protons circulating at the Large Hadron Collider. Ultra-high energy cosmic rays are likely accelerated to such monumental energies by powerful cosmic accelerators, like supermassive black holes and supernovae, located outside the Milky Way at distances of a few gigaparsecs and in the far reaches of the observable universe. They then traverse these cosmological distances and smash into the Earth. However, despite scientists' efforts, no individual source of ultra-high energy cosmic rays has ever been identified. That's because it's incredibly difficult to determine where these ultra-high energy cosmic rays are coming from. Cosmic rays are electrically charged, so they're bent by the magnetic fields that exist in intergalactic space and inside the Milky Way. As a result, the direction with which they arrive at the Earth does not point back to their point of origin. While traversing the cosmos, ultra-high energy cosmic rays also randomly interact with cosmic photon fields that permeate the universe, including the cosmic microwave background. In these interactions, ultra-high energy cosmic rays are either completely destroyed and so never reaches at the Earth, or lose a significant amount of their energy, which further aggravates their magnetic bending. So how can we ever determine where these ultra-high energy cosmic rays are coming from if they don't point back to their source? Well, ultra-high energy neutrinos may provide a workaround. Neutrinos are incredibly light, electrically neutral, and hardly interact with matter, and never directly with photons. Neutrinos do not bend in the universe's magnetic fields, nor are they destroyed or sapped of energy in interactions with cosmic photons. They are able to reach the Earth even at the highest energies and from the most distant of locations. It's likely that neutrinos are produced in interactions in dense environments around ultra-high energy cosmic ray sources. For example, when cosmic rays are accelerated in the vicinity of a black hole, smash into accreting matter, and produce ultra-high energy neutrinos that stream towards the Earth in straight lines. These neutrinos point back to individual sources when detected at the Earth, so they're capable of revealing individual ultra-high energy cosmic ray sources. In 2017, scientists at the Ice Cube neutrino detector in Antarctica traced the path of a single high-energy neutrino to a previously known but little studied blazar, TXS 0506 plus 056, the nucleus of a giant galaxy that fires off particles in massive jets, powered by a supermassive black hole at its core. However, we need far more examples to be confident that such phenomena really do give birth to the highest energy astrophysical particles. The pursuit of high and ultra-high energy astrophysical neutrinos also has many more benefits in both astrophysics and particle physics. If you would like an in-depth introduction to the importance of high-energy astrophysical neutrinos, you can check out the relevant timestamp in my video here. The bottom line is that detecting high-energy astrophysical neutrinos is an incredibly important part of the new era of multi-messenger astronomy. Neutrinos are a new lens through which we can look at our universe, one we are just beginning to peer through. So, what is the ARCA array, and how can it detect the highest energy astrophysical neutrinos hitting the Earth and determine where they're coming from? ARCA is an array of the Cubic Kilometre Neutrino Telescope, KM3-NET, the successor to the Antares Neutrino Telescope. The KM3-NET collaboration comprises more than 250 scientists from 16 countries, including France, Morocco, South Africa, Australia, Georgia, China, and the United Arab Emirates. KM3-NET is comprised of two detector arrays: ARCA, the Oscillation Research for Cosmics in the Abyss, located at a depth of 2.5 kilometers offshore from Toulon, southern France, and ARCA, the Astroparticle Research with Cosmics in the Abyss array, located at a depth of 3.5 kilometers, 100 kilometers offshore from Sicily, Italy. ARCA is a 7 megaton dense detector optimized for the detection of sub-TeV, atmospheric neutrinos. ARCA is a more sparse array with an instrumented volume of water of 1 kilometer cubed, and is optimized for the detection of higher energy TeV and PeV, high energy astrophysical neutrinos. All told, KM3-NET promises to be the world's largest neutrino telescope. ARCA's Mediterranean Sea location allows the array to observe 87% of the sky, including most of the galaxy and the galactic center, and provides complementary observations to the Ice Cube detector located at the Earth's southern pole. ARCA is composed of a three-dimensional array of pressure-resistant glass spheres about 0.5 meter wide, housing photomultiplier tubes for light detection, several instruments to determine the real-time position of the sensor modules, and electronics to calibrate measured signals. These sensor modules are known as digital optical modules, or DOMs, and are arranged in vertical string-like detection units, or DUs. A total of 18 DOMs are hosted on a single 800 meter long detection line, and the lines are anchored to the sea floor and held taut by a submerged buoy. ARCA currently has 18 detection unit strings deployed, with plans to deploy 230 over the coming decade, and has been collecting data since the mid-2010s. Okay, so ARCA is a really cool detector and a brilliant feat of underwater engineering. But how does it detect astrophysical neutrinos? And how did it detect the highest energy astrophysical neutrino ever? Well, in the dark abyss of the Mediterranean Sea, ARCA can capture the light produced by high energy charged particles traversing the transparent seawater. When high energy particles pass through a transparent material faster than light can travel in that material, they produce a shockwave cone of light known as Cherenkov radiation. Remember that although the speed of light in a vacuum cannot be exceeded, light slows down in denser media like water, meaning that high energy particles can outpace it in those media. It is Cherenkov light that produces the ghostly blue or green glow observed when high energy particles from nuclear reactors traverse pools of coolant water. You can think of it like a kind of sonic boom, but for light instead of sound. When planes break the speed of sound in air, they emit a sonic boom of sound. When particles break the speed of light in a medium, they emit a shockwave of light. When an astrophysical neutrino interacts with the seawater or ocean floor rock, it can produce charged particles like electrons, muons, or tau leptons that stream through the water instrumented by ARCA, producing cones of Cherenkov radiation. The light produced is sequentially captured by the photomultipliers in the ARCA DOM sensor units at different times, and this allows the trajectory of the charged particle producing the cone to be determined. Different types of charged particles traversing the array leave different Cherenkov signals. Muons are highly penetrating and tend to pass through the entire ARCA array without decaying, so they leave a single, sharp cone of Cherenkov light, indicating that a single particle, a muon, flew through the array. Electrons produce fuzzy, diffuse Cherenkov cones as the electrons crash into other electrons in the water and create a cascade of charged particles, each emitting a cone of Cherenkov radiation. Tau leptons produce a characteristic double bang signal, with a cone of radiation emanating from the point the neutrino interacts, producing the tau, and a secondary shower of radiation from the point the short-lived tau decays. When the type of charged particle traversing the ARCA array has been identified, we know the type or flavour of neutrino that must have produced that charged particle: an electron, muon, or tau neutrino. The energy of the original neutrino can also be estimated by comparing the amount and direction of Cherenkov light captured in the detection units with simulations and theory calculations. The majority of the light that ARCA detects is the result of highly energetic cosmic ray particles, which produce showers of electrically charged subatomic particles when they hit the Earth's atmosphere. These showers contain particles such as muons that pass through kilometers of water and can even reach the depths of the ARCA array and traverse it before decaying. So how can we separate high-energy astrophysical neutrino events from this background? Well, we're used to being told that neutrinos pass through everything and very rarely interact. And that's certainly true for low-energy neutrinos. Low-energy neutrinos could pass through a light year of lead, and only half of them would be stopped. Trillions are happily passing through your body right now. However, the probability of a neutrino interacting with matter and being stopped increases as the energy of the neutrino increases. And for high energy and ultra high energy neutrinos, the Earth becomes incredibly opaque. Essentially, all the high energy neutrinos crashing into the Earth are stopped by it. That means that high energy neutrinos that just skim the Earth are very likely to interact in it. If these neutrinos are muon neutrinos, they will produce highly penetrating charged muons that are very likely to punch out of the thin strip of crust in which they were created, and then have the ability to traverse the ARCA detector in a horizontal direction. This leaves a thin strip of sky just around the horizon where Earth-skimming neutrinos can be detected and easily identified as high-energy astrophysical neutrinos. And ARCA just captured one such signal, a particle with a mind-boggling amount of energy. Recently, 1/3 of ARCA's sensors recorded bright, sharp flashes consistent with the Cherenkov cone produced by a muon crossing the array horizontally. The muon must have been produced by a muon neutrino that arrived from around 1 degree below the horizon. Simulations indicate that it's very unlikely that a muon, even with an energy of 10 peta-electron-volts crossing the ARCA array, would have created the sheer amount of light observed in this event. The upshot is that the most likely interpretation of this event is that a muon neutrino with many tens of peta-electron-volts smashed into the Earth, creating a muon with an energy far higher than 10 peta-electron-volts. Such a characterization would make this neutrino the highest energy neutrino ever detected. Until recently, only IceCube had the capability of seeing these extreme particles. That makes this detection by the much smaller ARCA array all the more sensational. The initial build phase of ARCA appears to have already won the lottery. So, what now? What else can we learn from this amazing particle? And where do we go from here? Well, given the layout of the ARCA array and the transparency and low optical scattering of deep sea water, the direction of muon neutrino events in ARCA can be reconstructed to an uncertainty of less than 0.1 degrees. This superior angular resolution will narrow down the region of sky that traditional telescopes will have to search to identify the potential cosmic accelerator that produced this phenomenally powerful particle. Unfortunately, at the moment, Coelho has offered no indications of the trajectory from which the muon neutrino arrived, nor exactly when the observation occurred. So we currently have no clue whether this neutrino points back to an energetic astronomical source. Coelho has promised more details to follow, but doesn't want to tip off potential academic competitors. In the meantime, we will just have to wait. And there's much more to come from ARCA in the future, because as they say, one high energy neutrino doesn't make a summer. As ARCA expands, it will be looking to capture more high energy astrophysical neutrino signals and look for statistical excesses of such signals emanating from certain regions of the sky. These excesses can then be correlated with the locations of highly energetic astrophysical phenomena observed via traditional photon telescopes. ARCA will seek to determine whether high-energy cosmic neutrino sources are point-like or diffuse, constant or transient. The KM3-NET collaboration has shown that they have developed robust hardware, reconstruction techniques, event selections, and statistical frameworks to identify high-energy astrophysical neutrinos and determine their characteristics. Now they need time and statistics. They will not be alone. At least 4 more observatories capable of detecting the highest energy astrophysical neutrinos are under construction or planned. The golden era of neutrino physics has begun. Until recently, only IceCube had the capability of seeing the highest energy neutrinos traversing our universe. The ARCA array is only 10% complete and has already detected the most energetic neutrino ever observed. This solitary event may have been a fortunate fluke, but it shows the power of ARCA and the promise that it holds when fully realised. Soon, ARCA will begin sending real-time alerts to its multi-messenger partners, including conventional photon telescopes, but also other neutrino telescopes such as IceCube and Baikal GVD, when a neutrino candidate with a high probability of astrophysical origin is detected. Such a worldwide high-energy neutrino collaboration will allow scientists to confirm the detection and trajectories of the highest energy neutrinos traversing our universe with precision. With 3 major neutrino telescope facilities now online, Baikal GVD, IceCube, and KM3-NET, the future of neutrino astronomy is truly bright. Particle physics is full of exquisite symmetries. Using the pitch black depths of our planet to chart the inky, unknown depths of our universe, is a beautiful example. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.